So good afternoon, everyone. Let me kind of go as usual with announcements. Um, I'll start with maybe the most important one would be the next homework, and then I kind of work my way through the rest of them. So homework 4 is here, 4 out of 5. So we after this one, we have one more. And I was telling you at the beginning of the semester, as we go towards the end, at the beginning they were kind of very open-ended. Now these tend to be more restrictive in a way. I feel like the homework. So this is more restrictive, but also probably the closest you can get to to an objective evaluation this semester. So it'll become clear in a second, but this is pretty close to. There is some room for such subjectivity, but not that much. Okay, so on this one, I'm providing an adjacency matrix for a graph, and I know since this is a visualization class, we talk about graphs more. There, it kind of has at this point it'll have two meanings. One is being a chart of some sort. It's a synonym to graph, but also graph is a kind of mathematical construct where we have a binary relationship between two elements of a set. So another way to think of it is a network. So in discrete math, a graph is what we call a network in other places. So that's kind of what you're getting here. So this chapter, the term graph really means a network. And one of these adjacency matrices, the way they work, they provide a binary connection between two things. It's like two people talking on the phone. Um, there's other relationships that are not binary. So for example, if we are in a, I don't know, conference room, then we can have 10 people in that relationship. So it's not the same thing as each person talking individually with another person. Is all of them are together. So that's kind of, these are two examples of things that have relationship in them. But for the graph, it's the least relationship we can think of because it's binary, so it's just two of them. And on this adjacency matrix, I kind of give you a graph typically has some nodes and some links connecting those nodes. Kind of going back to chemistry, it's a stick and ball diagram. It's a node link diagram. That's one way to visualize these graphs. And in this case, this is not a visualization. It's just an adjacency matrix, and it kind of tells us that we have 10 nodes. These are the names of the nodes. A few years ago, somebody tried to give them names, but the names are already given there. The first node is 1, the second node is 2, and so forth. So you can see the nodes, they're on the columns and also on the rows, the same nodes. And the way this adjacency matrix works is that, for example, here, if there is a 0, basically says there is no relationship between 1 and 1. There's no relationship between 2 and 1 or 3 and 1. So basically 1 is connected to 6. That's the one that we have here. I'm also telling you that this is an undirected graph, so it's not from 2. It's like these two talk to each other. It doesn't mean 1 and 6 talk to each other. It doesn't mean that 1 goes to 6 or 6 to 1. However, because a matrix is square, what's going to happen here is that 6 and 1 must be connected. If 1 and 6 are connected, 6 and 1 are connected as well. It's undirected, so there's no direction on this connection. So unless I messed up, because I kind of built this more or less manually, this adjacency matrix, it should be, the matrix should be, how do you call it? Symmetrical around the diagonal. So in other words, if I have a 1 and 10, I'm supposed to find one at the other end, 10 and 1, and so forth. You kind of see here 3 and 2, 2 and 4, and then same thing here, 3 and 2 and 2 and 4. So that just because it's a matrix and it's square, that's the only reason we have two ones. But they represent the same undirected relationship between two of these nodes. Okay, so that's kind of what's given to you. Again, it's just a relationship, a binary relationship, and it's undirected and it's very simple. Nodes are either connected or they're not connected. And what the whole purpose here is kind of to have you think a little bit how complex drawing some of these graphs can be. And this is a relatively small graph, only 10 nodes. And notice that there's a lot of zeros, so there's not a lot of edges or links between these nodes. But what I want you to do is draw a visual representation for this graph, for this network. So if you have two choices. You can use some general drawing program, so programs that will allow you to draw anything, like Paint, PowerPoint, anything else, or you can try and do it by hand on a piece of paper, but make sure it's neat. Again, remember how people can understand what you're doing in there. So both of these are perfectly fine. What's not allowed, where is it? What's not allowed is automated graph layout tools. So by that, there are some programs, and people try to write them, and I think they have their own conference every year. They get better and better. But there are programs out there that would draw the graph. And what I say by layout, it means it decides the same things that you would need to decide for this homework. It decides the position of each node. It decides the size of the node. It decides the edges or the links between the nodes, how they go, the routing. So sometimes these edges go straight, sometimes they may go around something. So there are automated layout tools that would do that. But for this homework, what I want you to do is kind of do this manually. And so here is the criteria, really. So we need, try as much as you can, make the graphs that you draw conform to the goals for graph drawing. And I'll pull up that slide. And it should be right about here. If I remember correctly, it's lecture 6. I'll go back to the homework. Oh, I'm in this one. And homework. And then let me pull up that slide right here. So slide 9 comes up with 3 goals for graph drawing. Let's see what will allow me to present. It won't let me do I think I have to enable editing before it will let me draw on it. So there are these 3 graphs for these 3 goals for graph drawing. So we need to reduce the intersection. So intersection can be between 2 edges, 2 links, or a link kind of going on top of a node, or even between nodes, depending on how that's structured. So we would like to, so that's one goal here, reduce the intersections. The other one is reduce the variation why do we want to reduce the intersections? If you think about it, occlusion. We don't want to cover stuff in the graph, and we don't want to get different ideas. So for example, if I have two nodes like that, I'm not sure why the pen kind of went that way, and I have a link that goes over this node. Now the question is the edge that I drew intersecting this node, or is just passing on top of it? So it creates kind of maybe the illusion of an incorrect graph or something like that. So that's why we want to reduce intersection. The other way is if I have a lot of intersections, a lot of edges that intersect, it's going to be really hard to figure out which nodes are connected to which nodes. I'm just making it on purpose look really bad. So that's why we want to reduce intersection. That's kind of a reasonable goal. And the next goal would be to reduce the variation of lengths for our links, for our edges. In other words, if I have a graph where all the edges are about the same size, and again, I don't know why it does that. It allows me to focus on kind of how far a node is from another node. So if this is I'm kind of focused on this node, and I see something going on right here, if the links have about the same length, it kind of tells me that this node here is a lot further away than this node here. So I can kind of guesstimate things that are close, things that are far. If I have edges that have kind of different lengths, I can have an edge that's, it's about 10 times longer than the other ones, then I can tell how things, I can get this idea of how close two nodes are that are not linked to, connected to each other necessarily. And the final one, really almost kind of related to this, is related to both of them, is to reduce the bends. So the straighter the links, the better. If I have edges that are about the same, but some are straight, some are bent, it still creates kind of weird possibilities and illusions. Okay, so these are the three goals for homework 5. We need to reduce the intersection, how many things are on top of each other. So like I said, one intersection may be this, just to be clear. If I have two of these links intersecting each other, then why should I have that instead of maybe having it in parallel and I can avoid it? No, it's not going to happen for the homework because I don't have all the nodes are connected to each other. So I have component, it's called connected components. So basically starting from every node in that graph in the homework, you can reach every other node. It's not like there's an ocean in between, but here is an example of intersection. Reduce that. We want to reduce how the variation between the lengths of each link. Ideally, we'd have no intersection. We would have all the links be the same size, same length, and none of them would be bent. So we want to have links going straight. You can have links that go in really weird way, like going all around. And it's going to make it really hard. It's like one of those kids' mazes that they have to solve. So we don't want links to be like that. We want them to be straight. And we want them to be the same size, and we want them to reduce intersection. I think I said it about 3 times already. But for your reference, that's slide 9 from lecture. Slide 9 from lecture 6 is what this homework refers to. Okay, so we need to make that's basically your measurement, your goal right here, your criteria, that's what you should be striving for. It may not be possible, again, in discrete math, these graphs, they've been studied, and they're called planar if there is a way to draw them without intersection. There are some graphs that are not planar, and you cannot draw them without intersection. I don't know. This one is a new one. I just made it this semester, so I have no idea if it's planar or not, but we'll see what the results that we're getting, and then we'll figure it out. I'll get back to planar in a second, kind of more FYI interesting stuff. A planar graph is a map, can be put on a map. So all our maps are planar. Why? Because they're on a surface, on Earth. And we can always draw a link between countries, no matter how the map is made. But not all possible graphs are planar. When we start adding edges to them, more links we add to them, at some point we have too many, and we cannot avoid intersection at least one or more. So I don't know about this one, what the intersection is going to be, but we'll figure it out. You try it, put it on paper, and try and see how close you can get to satisfying those. And again, like I said here, it may not be possible to satisfy all that. Optionally, if you satisfied all the goals and you have 2 or 3 designs, I don't think most people are going to run into it, but find the one that's more interesting, if you have a choice at that point. So what I want you to submit is the graph visualization. And then again, it's an optional paragraph. If you have a strategy that people, you're proud of, put it there. It doesn't have to be a whole, I started with 1 node, I added a link and put the second node, and then you display the graph with 2 nodes. And I don't want to see how it was built. I don't want your peers to necessarily have to look at that. So all I'm asking is show us the final version of that graph. And even if you don't write anything, that's also going to be fine. And like I said, there are 2 ways you can. Neat handwriting are fine, and the general drawing program is also fine for this one. My handwriting is really bad, so I usually go. Plus, if I mess something up, I fix it while on a computer. I can always fix stuff and move it around. Okay, so that's kind of what we're looking for. There will be, like usual, peer review, but the criteria here is going to be the most objective criteria so far. I mean, this semester. Homework 5 goes back to, I couldn't find an objective criteria for it. So kind of here I'm starting the opposite as others, but if this is, not a graph or something, or you only see 3 nodes and you don't see the other 7, and that's missing for sure at that point. And the other way where you can lose a lot of points, especially now when you're working on this, please make sure to not do, I see somebody. Okay, so I'll get back. I just read some of the comments. 323, so that was. Do I have an example? I already, Lester already have an example. I had. This is an example of a node link diagram. Now there are fancy nodes with people in them. There's no need for this homework. This is another example of, no, we have node, link, link. So that's a node link diagram. Hopefully that explains it. So node link. You can see various things for these nodes. Actually, some of it I have in the lecture slide. So all of these are node link diagrams. We have a node and we have a link that kind of shows that. Now, obviously, there's 2 intersections right here. between these. So try and make those, try and satisfy those goals as much as you can. What you can do, again, you can move the nodes around. You can lay them out, move the nodes around, decide, their shape, their size, whatever you can do in there. Move the links around. And in other words, what's the path for those links? They don't have to be, the goal is to be straight, but, and so I'm kind of forcing you to be straight, but maybe you can find something where one of them is not straight and you avoid an intersection. Normally, if I go around the node, I can avoid an intersection that way. Okay, so that's, hopefully that, so yes, I want, okay, I think you said got it, thanks. But this, please double, triple check your submission. I still have, and I don't know how it happened. Apparently it's easy to happen, so that's why I said triple check your node link and make sure you have all, most people are gonna have those 10 nodes, but make sure you have all the links as they are laid out here. So read through this and check your drawing and make sure that your drawing will have an edge between 9 and 6. Don't miss it. Some people miss it. Some people add new stuff. For example, they will have a link between 9 and 7. And that shouldn't happen. That's 100% under your control. And it should not happen, but again, it still happens, I think, at a rate, every semester I see it at a rate way too much. Maybe wait to the last minute or something, but really should not happen. So please, please, please check your solution with the adjacency diagram that's in there. You should not run into this situation. You control this. There's nothing that you can control. If a link is missing, put it there. If you have an extra one or a wrong one, put it there. But otherwise, reviewers are going to look for that, and you're going to get a 0. There's no reason to get a 0 for that. So you can control it. The other thing is, yes, I'm asking for a node link diagram. There are a few other ways, not very, for example, heat maps could be used, but I don't want a heat map and I don't want a matrix. In other words, it's not going to help you like homework 1 to take this matrix and just put some color on it. It needs to be a node link diagram. Most people don't have trouble with it. I haven't seen it in many years. So node link is node link. I kind of showed you the example. And this is kind of keep it anonymous, just like I've been trying to do this entire semester. And notice I still have the author property in there. Sometimes the operating, you kind of saw how some operating system expose it, others hide it. So you have to look for it. And I showed something on, we were talking about homework 2 review, I think. It's recorded. I don't exactly know exactly where that is. Now, so these are all kind of cases we shouldn't run into. And then as far as the actual, meat of evaluating this, so if that graph conforms to all 3 graph drawing goals, just write all goals and give it 4 points. You can give 4 points. I'll talk about it again when we do evaluations for this, but you can give 4 points to to everybody. If their graphs are perfect, you can give everybody 4. So on this one, notice there is no restriction. There is no restriction to how many 4s or 2s or 3s you can do. Again, I think this is a more objective criteria that everybody most people should be able to agree on most of the time. Okay, 3 points for graphs that largely conform but have 1 intersection or 1 unusual link or 1 bent link. Okay, so one intersection is pretty obvious. If you see an intersection, it's an intersection, and but only one. If they have more, and it doesn't qualify for a tree. Now, what if the graph? You may ask, what if the graph is not planar, which means there is no way to write it to do it without an intersection? Follow the criteria and give a 3. What I would do when I take the raw score, I will add that extra one. I would know it was impossible to get a 4, so a 3 is as good as anyone could have gotten. And I'm going to go ahead and add it. So your raw score will have that added to it. So just follow the criteria on this, regardless of whether the graph is planar or not. So whether you can do it without an intersection or with an intersection. If there is one intersection and only one, that's a 3. If one of the other thing I want to point out, if one of the edges is longer or shorter than the rest, it's also a 3. Now, I don't expect you to get a ruler and measure it to 1/32 of an inch or count the pixels that are spanning that link. It's a visual thing. If they appear to be the same size, they are the same size for all practical purposes. Okay? Visually look at them and you kind of see, are they about the same? Again, it's not, I don't expect you to, it's a visualization class. So if people perceive it as equal, it is equal. That's a little bit of, maybe a little bit of subjectivity right there that can be introduced. I get that. So I was telling you, it's as close as you can get to an objective one, but here it's just by looking at them, can you tell they appear the same length or they appear different lengths? And so if one of them is long or short, that's a 3 as well. Now 2, and it's a little bit more subjective on this one, but if it's more than one thing, more than 2 intersections, or maybe there's one intersection and one long edge. So if it's more than one, that's what I mean. If it's more than one violation, it's not going to qualify for 3. But if it's a few, then it qualifies for a 2 at that point. And finally, if it looks like it's completely random, somebody didn't just drew everything. We have 5 intersections and edges are all over the place in length, or maybe they're all bent around it, none of them is going straight, or most of them are not going straight, things like those. So there is a little bit of, again, subjectivity between 1 and 2, but it shouldn't be any subjectivity for 3 and 4. Or just a little bit, I guess, on how you view the links. But if it's one of them is obviously different, then it's a 3. If we have 2 of those, then think about a 2. Obviously, if it's only 2 of those, it's a 2 for sure. It cannot be a 1. And then if there's a lot of them, of those violations of the goals, that's going to be a 1, kind of more like random, like whatever you would consider. It's completely random. Yes.
You mentioned a long boundary, so you can't do like an XY diagram. That's not.
This is not an XY diagram because we have a node link. We have nodes and they links between the nodes. So by the long, I mean, I didn't mean the links in math, in discrete mathematicians, they call them edges. That's where the edge comes from. An edge is a link. And if we do in visualization, many times we call them a link. We have a link between 2 things. Or in networking, there is a link between 2 servers. But mathematicians would call those edges. That's where the edge is coming from. So there's not the edge of an area. An edge is the same as a link, if you hear me say something like that. And again, this construct is not necessarily a visual construct. At the end of the day, it's an abstract thing that comes from math. It has a lot of visual things, like we have roads between here and New York. You go through Nashville, and so there's one road connecting Little Rock with Memphis, Memphis with Nashville, and so forth. So there's a lot of physical realities of that, but at the end of the day, this is a mathematical sense. And again, if you hear me say edge, is the same thing as a link, the connection between two nodes. A binary relationship, that's what it is. Okay, so I'll cover this again, but just so you know, I wanted to make sure that you understand that for this, it's 100% almost in your control how this gets drawn, and make sure you don't fall under this one. Double, triple check your final result to make sure it is exactly what's in here. Go through each and every node and make sure it's correct, connected to to all the other nodes. That's supposed to be connected, and no other node. So I've seen it all over the place. Sometimes there's an extra, sometimes there's one missing, sometimes there's a completely wrong one, like between 3 and 2. In this adjacency matrix, there is no connection between 3 and 2 because there's 0 right here. Oh, I'm wrong. 3 and 2 are connected. Wrong example. Strike that. Between 2 and 1, there is no connection. So if you accidentally draw a line between 2 and 1, I don't want you to do that. You should be able to see it and avoid getting this 0. And again, I will emphasize when we go to the review for this, the whole thing, that it is almost the most objective thing we will do this semester. I think I'm reaching the end of this. Not sure if I missed much on this. So that's about homework 4. I'm still, I know I owe you homework 2. I'm making progress on it, but I'm not done with it. I haven't even started on 3. But 3, which was your reviews, should have been done today. So I know it's waiting for me to kind of take a look at it, but I'm still working on 2. Once I'm done, it will show up. And that's all I have about the homework. Oh, I'll say it, if you look at it, it's in 2 weeks. Well, here, actually, that's the right one. Both are the same. Both dates are the same, but this is due in 2 weeks. Why? Because next week we have spring break. So spring break means no classes, virtual or in person or of any kind. So it's a break for everyone, and there won't be any classes. That's kind of normal university policy. And that's the reason we have a little bit more time on this one. It just stretches past. Unfortunately, it's right after spring break, so make sure you do it early. Maybe do it before, but it's right now. The deadline is right after spring break for it. For those of you who enjoy spring break, make sure you do it before if you can. Okay. So other things on this week, the week of March 17, we're kind of starting with graphs. So lecture 1 through 14, lecture 15 through 23rd. So it's pretty much broken down, but it's this first part of lecture 6. So about 23 of those slides that I kind of planned for this week. It should cover enough for the homework, and I already kind of covered that part.
Is there a quiz?
There will be a quiz. Towards the end of semester, we kind of skip 1 or 2, but the quiz is going to be due, let's check, but it's still going to be due right after spring break. March 31st. So you don't have to do it. There's not going to be any due material. It shouldn't be unless I messed up in Blackboard. And if you see it, let me know. But we shouldn't have anything due during spring break. So spring break is like a black hole. It doesn't, not even a black hole. It's just a hole. It doesn't exist. It's as if those dates don't exist. So you shouldn't, on my course, shouldn't see anything due. If you see it, it means something is wrong me programming it. Okay, so yes, quiz 7, it's going to be due in 2 weeks as well. And lecture slides, like I already pulled lecture 6, so it looks good on there. There's some videos that show you different ways of dealing with graphs, and nothing to do with the portal unless you really want to. Quizzes. Let me get out of this mode and look at last week's quiz. I want to just cover it. So it should be this one. Okay, so for this one, let's see. By the way, there are a couple of questions that have this thing. I tried to fix them, but when I try to edit, I don't see this. So maybe a new version of Blackboard shows it, but I gave up a couple of years ago trying to fix it. But it's not the right answer, FYI. It's just, it's always going to be one of the other 3. I think there is one more the whole semester, so there's maybe 2, possibly 3, but I don't think so. So some of these techniques tend to emphasize individual objects. Like an object, think about a baseball player, has, you know, a batting average, has an age, has, you know, salary, the team that player works, you know, plays for. So there are some techniques that focus on object visibility. So a baseball card is really based on objects. If I have 100 players, or I will have 100 cards, and I can see pretty good details about individual players, but I won't be able to focus on a single attribute. For example, it'll be really hard to see what the salary range is. That's what I mean. Not only me, but that's kind of what it's meant by attribute. So if I have attribute visibility, I'll be able to easily tell the salary range. And if I have object visibility, I'll be able to easily focus on individual players in my example with baseball. So these are kind of, and it tends to be that, again, it's hard to prove a negative, but it tends to be that some visualizations focus more on objects. Others, like baseball cards, focus more on objects. Others, like if I have a histogram of all the salaries, focus more on attributes. So that's kind of what this question is asking. So which of these 3 has attribute visibility? And it's going to be the parallel coordinate plots. Again, I assume you went through and looked at, see what they are. But star plots tend to show individual objects. Cherno faces tend to show individual objects. And parallel coordinates tend to show attributes and how they relate to other attributes. It's kind of hard to see an individual object in a parallel coordinate. And for star plots and Cherno faces, sometimes it's hard to see an individual attribute without having to scan and remember stuff. So that's kind of, I know there's like 3 or 4 of these questions, just all kinds of different types of visualization, but mostly focused on these. Kind of the same thing. Oh, no, this is different. Another way to break down these visualization tools, so one way is that one where we look at attribute versus object. Another way is which ones are more suited for statistics. In statistics, you don't want to be biased against an attribute or another. So you don't want to focus more on salary than on age. when you do some statistical analysis wants that. Some visualization tools are more neutral in the way they, or not biased. Others emphasize a certain attribute versus others. So which of the ones, that's the question asked, do not emphasize one data attribute over another? So parallel coordinate plots and star plots tend not to emphasize, and I think Attribute Explorer doesn't do it as well. So really the only one, I could have asked the same question, the opposite would have been a single choice. But Chernoff faces tend to, in Chernoff faces, they use like a human face, like a drawing. And the first thing you notice about the Chernoff face is probably the size of the head. But they also have eyes and nose and pupil. So there may be an attribute that's shown by the size of the eye, but that attribute is going to be harder to explore than the size of the head. Size of the head hits you, you see it immediately. Size of the eye is going to be harder. So from that sense, if I decide to put the salary as the size of the head and the age as the size of the eye, I'm going to be able to see variations in salary a lot more. So I'm kind of biased towards salary. That's kind of where I'm going for. And FYI, I think a lot of more of the visualization tools that and that's a personal opinion, everybody should have their own and different than mine, but a lot of the cool visualizations tend to be biased. A lot of kind of the more boring ones tend to treat all the attributes the same. Again, my 2 cents there, and it's not quantifiable at all. Okay, here let's talk about color schemes. And we have grayscale, full spectral scale, and double-ended. So actually, the way it's set up here, one good thing here is things that have both positive and negative values. That would be a double-ended scale. It's like you see positive numbers are red, and then negative numbers are green. It's something you would see on a map. The ocean is blue, and then the land is green. So it kind of shows negative altitude versus positive altitude, sea level, below sea level, above sea level. So that's a double-ended multiple hue scale. So that's going to correspond to A. Now this one, maybe not that clear, but to me this one is a lot clearer. So which color scheme doesn't allow us to put categories in order? Is it going to be the grayscale? Can I order something that's darker versus lighter? I can order them, medium, and so that shouldn't apply to gray. Also, full spectral scale means red, green, blue, yellow. Is red before blue? Is yellow between green? And so for the full spectral scale, it's not easy to put categories. You're not able to put an order to the colors. It's easier on the grayscale. So I would select C for this because it kind of that tells me. And then B makes sense as well. Grayscale is not the greatest scale that we can find. Sometimes having blue scale, levels of blue rather than levels of white and black can help better for different things. So that would be B. That's kind of that one. This is, again, you have 4 tries. Everybody should have gotten this. Yes, quantitative data can be shown imprecisely in a good visualization. Sometimes if I show too much precision, imagine showing all the numbers. I show you, 20 numbers of pi and compare it with some other real number, 20 numbers of some other real number, but that starts with 3.14. It's just, it's kind of hard. The more, sometimes precision is in the way. It kind of creates the idea that it's noisy when it may not be there. So it all depends on the task, on number 4. Which of the following has attribute visibility going to that? So it's going to be these 2, parallel coordinate plots and Attribute Explorer. Star plots are like Chernoff faces and multidimensional icons. They are object. they have object visibility. And so object visibility are going to be these two. It's kind of the opposite of those. And if I have more than 10,000 items, can I use Chernoff faces? If I have 10,000 people to look at, do you think we can understand anything? Not much. Parallel coordinate plots, they tend to become a hairball. If I have 10,000 objects in there, they tend to kind of be on top of each other. It really looks like a hairball. Star plots, same with the Chernoff faces. I would need to have 10,000 of these star plots. So really the only one that from that slide set that kind of can work is this visualization of relevance. And the original purpose for the visualization of relevance was to look at small databases, so 10,000 databases in general, and understand them. And this one talks about selective magnification to look on a map. And the idea there is we use a map, but then we take some pieces of that map, like some countries, and multiply them or shrink them based on some data. Like there were examples in the slide shows where we looked at trade, how much industrial exports a certain country provides. So we can take a small country like Japan, but it provides a lot. They export quite a lot of industrial. They have a lot of industrial exports, so they become almost as big as maybe Canada, and Canada or Russia, which is a big country geographically. But some of them get shrunk, some of them get expanded. But generally, they kind of follow the map in the sense that the neighbors, Japan is still going to be in Asia, it's not going to show up in Europe suddenly. Data values are not precisely shown unless you know ahead of time how big Japan is supposed to be. You kind of look at how big it is or small it is. You kind of figure out something that way. So data values are not going to be precisely shown. And then the relative position is generally maintained. Again, Europe is still going to have Germany and France next to each other, and Canada is not going to be close to India in any situation like that. So these two are the correct ones. Let me make sure I did not lie to you, but it's 1-1. Okay, so that's the quiz. Talk about homework. Project, keep working on it. There's nothing for a while on the project, but I still assume you're making some. So until April 21st, not much going on, but we will have the progress report then. As we get closer, I'll spend more time on it. Article presentations. We're going to start demonstration of visualization tools today. I'll see how many I got. I know I got some emails related to that, but I'm not sure I understood all the emails correctly, but we'll see. But you'll start getting some of these now. And article presentation, just go ahead and follow the schedule as is it posted in the announcement. And then I'll see how many of these I have today. So today should have been just one. So presentation of articles, we kind of continue for a few more weeks. But that's all the announcements today. I'll stop the recording. So.